Hydride ligands in organometallic chemistry. Hydride H- is the negative ion of hydrogen and does only exist under extreme conditions. Hydrogen has the electronic configuration 1s1, so hydride H- has electronic configuration 1s2 and has 2 electrons in the orbital s to be donated to the metal M. The bond MH is very important in organometallic chemistry for complexes LMH, while L is unsaturated group. The hydride can do insertion to this unsaturated group L and transform it to saturated one. For example, in the carbonyl metal hydride, the hydrogen can migrate and insert in the carbonyl to form COH, which is aldehyde group, and release a vacant site. By the same way, alkene MH, the hydrogen will migrate to alkene to form alkane M vacant site. So the hydride in organometallic complexes is the key to transform the carbonyl C triple bond O to aldehyde groups C double bond OH and the transformation of alkene to alkane. In 1931, Heber prepared H2FCO4, which was the first metal hydride complex. To study the bond MH, so the electrons of hydrides are donated to M, and M has lower electronegativity than hydrogen. That will give to the hydrogen the property we called hydridic property. Hydride H- is anionic 1- and is 2 electron sigma donor by the orbital s. Hydride can bound to one metal or can be bridging between two metal centers mu2. To explain the formation of the bond MH, the hydride has orbital s2 and M has d orbitals in all directions. The best way of bonding between MH occurs between the orbital s and dz2 orbital of the metal center. The metal hydride complexes can be characterized by two techniques, the infrared and the NMR. The infrared is a good method to study the type of bond, MH terminal, or MH or H bridging between two metal centers, where we have difference between the stretching frequency for the terminal MH is about 2200 and for the bridging is about 1600. NMR is also a good technique to characterize the metal hydride complexes. After formation of the bond MH by donation the electron S2 to M, if the metal is rich in electrons and if the metal has orbital d partially filled, for example from d1 to d9, in this case, and in the presence of these two conditions, the electron density of M is more repelled to the hydride by back donation. And in this case, the proton NMR chemical shift for the metal hydride complexes will be in the shielding effect and in the negative ppm from -5 to about -25 ppm. And this is for the hydrogen of hydridic character. To note that the proton NMR for hydrogen in organic chemistry lays from about -4 ppm to 14 ppm. The complexes that do not have orbital d partially filled, for example, d0, no orbital d, or d10, which is completely filled, the chemical shift in proton NMR were observed at the positive value. Consider, for example, the complex Cp*2 zirconium H2. The zirconium oxidation state is +4. The zirconium 0 has S2, D2, or D4, so the zirconium 4 has D0. In this case, we don't have d orbitals containing electron density to be repelled to the hydride, so the hydrogen is observed at the positive chemical shift. For the complex HCU PR3 6, the copper in this case is copper 1, so the copper 0 has S1 D10, the copper 1 has D10 orbitals. This orbital is completely filled, which is highly stable, and the metal M would not repel the electron density to the hydride, so the chemical shift is also observed at the positive ppm. The experiment proved that we have some exceptions. Even the electron density of hydrides is high. Some hydride complexes behave as protonic acids in solution or in polar organic solvent. The complex HCOCO4, the cobalt, has oxidation state 1, so it's D8. By theory, we said the metal center from D1 to D9 will give chemical shift in the negative domain. So the hydrogen NMR observed is really in the negative domain. But when we put this complex in water or in methanol, this complex behave as strong acid that release H+, and the strength was similar to HCl. As a general rule, is the metal hydride acidic or not? We have to follow the electron density on M. When the electron density on M is poor, therefore, we would not have repel of electron density of M to the hydride, and in this case, since the metal center is poor in electrons, the hydride will give its maximum capacity to M. So the hydride will be less hydridic. That means we have less electron density around hydrogen, or in other words, we say the hydride will be more protic. So in this case, the metal center is more acidic of lower pKa. In this table, we present the pKa value for certain transition metal hydrides and to note that the behavior of the metal hydride depends on the solvent. For example, Cp chromium HCO3 has pKa 5.4 in methanol and 13.3 in acetonitrile. So in methanol, this complex, this metal hydride complex, behave as acidic. And this is also known in the chemistry of the solution. For example, HCl is a strong acid in the medium water. If you change the medium in analytical chemistry, if you change the medium of HCl and you use, for example, acetic acid, HCl will behave as a weak acid. So we have the same case in the metal hydride complexes where the acidity depends on the nature of the solvent used. Hydride is the smallest ligand, and as a result, we will have great overlap between the orbitals of M and H, so the distance, bond distance MH is quite short, is about 1.8 to 1.5 angstrom depending on the metal. In other words, the hydride in most cases could not be released from the metal hydride complex, only in one case when this metal hydride behaves as acid. But we will see in the next slides that the hydride can migrate from the complex or from the bond around M to another ligand present on M, and we say that this reaction is the migration of hydride to the ligand L or the insertion. We will talk in details in the next slides. The hydrides cannot be characterized by X-ray diffraction on crystals. And to note that the X-rays diffraction on crystals is the most important technique of characterization of organometallic complexes. Why hydride could not be observed by X-ray diffraction on crystals? This is due to the very small number of electrons on the hydride versus the adjacent atoms, especially the metal, and also due to the motion of hydrogen around the bond MH. The best technique is to characterize the metal hydride complexes is the neutron diffraction technique, and by this way we can observe the bond MH. Synthesis of hydride complexes. We have four or five methods. The best method is the addition of hydrogen, for example, to a complex MLN, and the hydrogen by oxidative addition. This reaction will be studied in details in the next chapters. So by oxidative addition, we will fix two hydrogens in position cis on the metal center. Sometimes, when we add hydrogen to the complex MLN, we did not obtain this structure. In this structure, we have MH bond and MH bond. We obtain MH2 bond. And this will occur when the metal center, when the electron density on the metal center is the right amount. So not too much, not too little. We will have M H2 bond. So when the metal M is rich in electron density and we add hydrogen molecule, we will fix two separated hydrogens or two separated hydrides on the metal center. And if the metal center has the right amount of electron density, so not poor and not rich, in this case, the H2 molecule will be bound to the metal center. How would the molecular HX or H2 bound to a metal? Suppose we have a metal center M and we add the bond or we add a molecule HX. To note that between H and X we have two electrons bonding. These two electrons bonding will be donated to M to obtain this figure. To note that in this type of bond, the electron responsible for the bond are the electrons bonding between H and X. And as you observe, we don't have bond M to X nor M to H, so we will have overlap between the electron bonding orbital and the d orbital of M. And this type of bond is similar to the binding of the lone pair on ammonia, for example, to a metal center. If M is rich in electron density, so we will have back donation from M to the orbitals H, X, and especially to the orbital sigma star of HX. The back donation occurs from the d pi orbital of M to the antibonding sigma star orbital of HX, and we will have breaking of the bond HX and formation of the bond MX and MH. And this type of mechanisms is similar to the back donation from the metal center d orbital to the carbonyl pi star antibonding orbital. The second method to prepare metal hydrides is the protonation of the complex, but the complex it requires an electron-rich basic metal center. For example, FeCO4 2-, we add H+, and H+ is bound to this complex, and we can add, for example, another H+. This type of reaction, the protonation, could not happen on all complexes. It happens on specific complexes with electron-rich metal center. The third method is to add a molecule that is hydride donor, for example, as lithium B-ethyl-3H, or in organic chemistry, you know that LiAlH4 is hydride donor. So you add these types of substances to the complex and you obtain metal hydrides. To note that this type of reaction will form several MH bonds, and the method 2, the protonation, will form in general one bond MH or two bonds MH. The method 1, which is the oxidative addition of hydrogen H2, will form two bond MH, or it form one bond M H2 molecule. So method 3, the interest of method 3 that it may forms several MH bonds. Method 4 is the addition of a ligand, then do the beta elimination, and I will explain later in separated chapter this mechanism, beta elimination. And the method number 5 is the decarboxylation. Consider this complex chromium CO6, add a base, we attack CO to COH, then we have migration of CO2 and appearance of the bond MH. So this is the general 5 reactions to prepare the metal hydride complexes.